All right, so our next topic is mineral identification, and this is something that you're all familiar with, whether you want to admit it to yourselves or not. There's always things in our lives that we're afraid to admit to ourselves and we're more familiar with than we'd like to say. But in this case, it's just minerals. So first, I'm just going to mention really briefly that there are a bunch of groups of minerals. Minerals have a certain definition we'll get to in a minute, but we tend to break them up into different groups. There's the carbonates and the silicates and so on. The biggest of which are the silicate mineral groups. And you're going to find this out in silicate mineral group. Sorry, there's only one silicate mineral group. You're going to find out in class over the next couple days that the silicate minerals are the majority of what we look at, because there's just, the other ones are small enough but they're silicates because they contain this, silicon dioxide. And we'll get to more details about that in a minute. First, what is a mineral? You'll want to commit this to memory. So write it down right now. Pause and write it down. A mineral is a naturally occurring, inorganic, crystalline solid with set chemical composition and characteristic physical properties. Couldn't have said it better myself. And those physical properties include things that you're all familiar with. The shape of the crystals, cleavage, fracture, hardness of a mineral, most hardness scale, specific gravity, which is related to density, luster, the color of the mineral, and the streak, and so forth. So, three common important minerals include, of course, quartz, calcite, and halite. But there are over 5,000 minerals that are out there. Here is a good example for the topic of hardness. Here's a great example of Mohs scale. So Mohs scale, as you all know, is a scale of 1 to 10. The Mohs scale is not a scale of absolute hardness. It just gives us an idea of how hard one mineral is relative to another. But it's a relative scale. But if we give minerals an absolute hardness, then we see how much harder diamond really is than corundum, which is our basic poster child for a 9 on the Mohs scale. So diamonds are orders of magnitude harder than even the next closest minerals, let alone all the way down here, lonely old talc. Okay? But really, diamonds are very, very hard. So this is what we call an absolute, this is the Mohs scale. These are some basic minerals at these different places. But this is how the absolute scale actually goes, and is, in reality corresponds to the Mohs scale. So there's the Mohs hardness, and then there's absolute hardness. Okay, using the Mohs scale, 1 to 10 here, I have an example for each hardness, along with its chemical formula. And then here's the absolute hardness. So talc is a 1 still. Calcite's a 9. But look at a diamond, 1,600 on the absolute hardness scale. Blows everything else out of the water. Now, what do we use? What do we use talc for? Well, maybe the first thing you think about talc is a baby's bottom, because that's what baby powder used to be made out of all the time. All right, so moving on to gypsum. What do we use gypsum for? Gypsum is used to make drywall. That's what drywall is powdered gypsum. So you all have it in your house, whether you realize it or not. What do we use apatite for? No, wait a second. Was that apatite? Sorry, that's calcite. Ah, yes, when we have indigestion, we tend to use calcite. We eat calcite so it can counteract some of the acid indigestion in our stomachs. Disturbing picture, perhaps, but all right. So this is, of course, this is fluoride. Fluoride is used to make camera lenses, and so this is an example of a camera lens that's got a fluoride coating on it. Apatite has nothing to do with what you want to eat, actually, but it's a great phosphate fertilizer. So those of you who have a farm or live on a farm or know farmers know that they're using apatite in their fields. All right, oops, wrong way. I'm going to make you guys sick. So here's topaz. Topaz comes in a variety of colors. Oh, I'm sorry, that's orthoclase feldspar. Ooh, getting ahead of myself. Orthoclase feldspar, hardness of 6, is mainly used as a gemstone. There's not much else it's used for. All right, and then the next one up is quartz. And I think I have a quartz. Yep, quartz. What is quartz used for that you guys use every day? Well, microchips. Yes, all of your phones and all of your computers and everything else use quartz Quartz is there. It's ubiquitous in our society, and it's also the most common mineral on the earth, which is kind of useful because we use it for a lot. Then there's topaz. Topaz, this is not a real natural topaz, but topaz is used mainly as a gemstone. This topaz has a coating to make it really rainbowy looking. All right. Oh, I'm getting ahead of myself again. So looking at, oops. Wow. All right, this is supposed to be corundum. Corundum is, when it's in a powdered form, is used as an abrasive because it has a hardness of 9. It's a lot more common than diamonds, so it's kind of useful for that. And finally, down to diamonds. Well, I don't have any special pictures of diamonds, but I think you all know what diamonds look like. So moving on to cleavage. Talk briefly about cleavage. Oh, I'm sorry, mineral crystal shape. That's what we're talking about next, crystal shape. So here's a bunch of different crystals. These are not really the crystal shapes we like to talk to in detail when we take mineralogy in college, but, well, dodecahedral is a good one. But this just gives you a rough idea of the fact, a rough visual to show you that crystals have different shapes. Next thing we'll talk about is cleavage and fracture. Sorry, I gotta get the right forward button here. So these are all exhibiting cleavage, and cleavage in minerals is basically the exhibition of nice flat surfaces when you break it. So some minerals have cleavage in only one direction. Other minerals have cleavage in multiple directions, 2, 3, 4, and so forth. All right, so then we'll move on to talk about streak. So here are two minerals, exact same mineral actually. It's a good example of why color isn't necessarily all that useful sometimes. But these both minerals, these are both hematite, both these samples have the exact same color streak. It's a brownish red streak on a streak plate. Okay, so that brings us down to streak. And we already saw how color wasn't very useful for those. Can be useful. This is how we take streak. So we take this mineral, we rub it on a unglazed ceramic tile, and we look at the color of the streak. Finally, there's also the reaction to acid, and you can see this little chunk of calcite being eaten up by the nasty old, mean old acid. Yep, pretty soon will be nothing there. We'll get to do some of that in class, hopefully. And now let's move on to the basic structure of the silicon minerals are the most common, so let's talk about that a little bit. Silicon minerals are made up of SiO2, and here's the silicon atom, and here's the oxygen. Now this looks like SiO4, doesn't it? 4 oxygens. Well, that's just because it's really SiO2, but these are going to be connected to another silicon next door. So you end up with this nice little tetrahedron shape. And those tetrahedrons can get put together in a bunch of different varieties. They can be just by themselves. They can be little bow tie silicates, but really we start getting into rings and single chains and double chains and sheets. This is like a mica, that's why mica occurs in flat sheets. Framework silicates, it gets pretty complicated. But the nice thing about silicon tetrahedrons is you can put them together in a variety of different ways. All right, well, looks like that's it. Those are the basics. So make sure you come into class ready to do some identifying, and we'll have some fun.